Right, can you hear me, Chris, everybody?
Yes, we can hear you.
Perfect. Okay, let's proceed then. This is a case history, which is more than 50 years ago, but it's a particularly simple case history. And the reason it's of interest is the following. If we look at our recent situation with tailings dams, we've had 6 large failures, which I'm sure you're all familiar with. And each one of these, when we have a dam failure, there's always a board of inquiry, you know, find the guilty, what went wrong. And it became necessary to use numerical methods to understand how these dams behaved. But the problem is, with doing this, that if we actually look at a lot of these liquefaction failures in the literature, the recent ones and also some of the older ones, quite a lot of them are actually caused by foundation failures or foundation movement. Liquefaction is very dramatic, but it's actually a secondary process. So that means, you know, as engineers, we have a lot of familiarity with limit equilibrium, but what the boards are saying, well, that doesn't work particularly well when we have a dam failure. But equally, when we look at the complexity of these dam failures, you might say, well, actually, you know, are you hiding something with these finite element methods? You know, what is special to make the, what required the finite element method? So it's helpful because these case histories are so complicated to look at something simpler to understand what is going on. This, what I've got on the screen now, I've taken you to northern Canada and to an area known as the Canadian oil sands. What we have there is actually more oil than Saudi Arabia, but it's locked up in sand in the form of bitumen between the sand grains. So what we do is we mine it with shovels and trucks, and we then basically cook it. And that is how we get the bitumen out. But that then leaves you with large quantities of sand slurry to dispose of, and that's the tailings. And what you see in the top right photo, which I've marked out in, hopefully you can see my pointer in orange there, that was the foundation of the dam back in 1973. Today, it is 100 meters high. And in fact, it's now closed out. So this is the same dam here as what we have down here, but, you know, 45 years later. And there's our tailings pond. This dam was built by upstream construction. And the guys, when they started doing this, they went through quite a learning experience. And what they had was a number of slumps. This was not dam failures going downstream. So it wasn't a failure of the dam. It was a failure of the raise when we're trying to construct out on the tailings. And they actually had 5 of those. But the one we're going to look at here is one of the largest slumps and one that was nicely documented at the time. This drawing here is from the engineer of record. That is their sketch they made after the event occurred. And we have a detailed loading history of how it developed. This was written up in a paper by Pluis O'Neill, McRoberts and Chan, and that paper became our reference for the documentation. One of the most surprising things about this slump was just how far it went upstream. And I'll come to that in a second. In those days, people were very much believed that the way to do safe upstream construction was to control the rate of rise. So the guys were putting in quite a lot of effort into looking at various rates of placement of fill over the tailings and how high they could go before they would trigger a failure. So all those blue dots are failures. And in the early 1970s, when this was being done, and keep in mind, this was people learning how to construct an upstream tailings dam. There was some laboratory strength testing, but there were no CPTs. It was very much I'd say in some ways, a fairly primitive engineering. Again, say it's early 1970s, but this dam has continued to be raised over the following 40 years. And as time has gone on, we've included quite a lot of high quality triaxial testing, and we've included lots of seismic CPTs. And we've actually got some pressure meters. So what we have is a case history, which is reasonably well documented, which is missing some of the data, but we place the same sands with the same methodology that they established in the subsequent 40 years. So what we've done with this case history, we said, okay, we'll take the information on what happened, which you reported, and we're going to look at these soil properties and the layering from the more recent testing, which I'm going to show you. But one of the most striking features really is how far it moved upstream. If you were to go and do a limit equilibrium analysis around here with an SU, whatever, or an SU, a sigma V ratio, whatever you want to do, the mechanisms that you'll get will be more or less a circular slip. And since this thing was only 12 meters high, you might only go about 12 meters upstream or thereabouts. It actually went more than 200 meters upstream. And so the first thing when you look at this, you actually might say, well, are these guys reporting correctly what happened? Well, I had an experience or opportunity to witness another failure, completely different dam. We're now over in Europe. And this is smaller in scale. This one was only 2.5 meters high, and it dropped 1.2 meters. You can see the back scarp here in the photo, and you can see this is the bench that failed. But what I observed was the enormous distance it went upstream. So I believe indeed what these guys are reporting is correct. That's a very key feature of this case history that we ought to be able to reproduce. Now, before I get into finite element analysis, I have to, oops, I've lost that. Let me come back, get that back again. Okay, I've got to tell you a little about soil behavior and how we represent soil behavior, because that's what we need in finite element analysis. And what I put on the screen here is a sort of thing you might measure in a triaxial test. So we're loading up a deviated stress here, and we're measuring axial strain here. And if we load up here and keep loading up and loading up, get to this point here, and then at that point I unload, what you'll find is you get virtually none of the displacement back. A little bit, but mostly everything is permanent. The permanent bit we call plastic, and that is the since you can see visually this is the dominant deformation. Clearly, understanding plastic behavior is key to understanding soils. Now, to do this, there's a formal body of theory known as the theory of plasticity. It was developed for actually started out almost for soils, but mainly developed for metals, and then we've adopted it for soils. Now, people say you're using metal plasticity. Well, no, we're not. We're using soil plasticity, and I'm going to show you the framework. To give you the background, when you take a piece of metal and you bend it and permanently deform it, the way it deforms is because what's called dislocation between the metal crystals have moved. In the case of soil, the way as particles move, we make and break contacts between the particles, how they touch each other. Mathematically, it's much the same thing, which is why the theory of plasticity works for soil as well as metals. Now, any theory of plasticity has three components. We have something called a yield surface, which is sketched in stress space, and that defines the area in which you can only have elastic movements, and then the stress conditions under which you start developing plastic strains. We have something called a flow rule, which tells you which way things are moving. Is it moving up, down, left, right, into the page, out of the page? In plasticity theory, we call it the flow rule. But if you think of elasticity, you'd know this as Poisson's ratio. It's the plastic equivalent of Poisson's ratio. And we then have something called the hardening law, which tells you as you accumulate plastic strain, the yield surface changes size. The equations and the rules of how the yield surface change size are called the hardening law. And broadly, you can think of that as Young's modulus. So in plasticity theory, we have different words for it, but we have the same ideas that you're familiar with from elasticity that you learnt at university. And critical state theory is an appropriate form of plasticity for soil for the reasons I'm going to show you. Now, where did critical state theory come from? You've mentioned my book in the introduction. Well, critical state theory is a lot older than me. It all started more than 100 years ago. Engineers in North America were using hydraulic fill construction when the cities expanded in the late 1800s. It was cheap, but they rapidly learned that a lot of these dams were falling down. In those days, it was called sand flow failure. The dam you're looking at here is Franklin Falls. It's about an hour's drive north of Boston on the east coast of the United States. And it was designed in 1935, built in the following few years. And this is the world's first liquefaction resistant dam. And in those days, it was called sand flow failure. And what they were guided by in developing this dam as a liquefaction resistant dam was this diagram down at the bottom here. If you can imagine soil and idealize it as ball bearings, spherical ball bearings, you can see here, this is the loosest possible packing of ball bearings, and any movement will have these ball bearings tending to collapse into the void space. If water is in the void space, you'll get positive excess pore pressures. This one over here is the densest possible packing of ball bearings, and any movement requires the balls to move up over each other and suck water in, or negative pore pressures. So the idea they had with this dam is, well, if this is very loose and this is very dense, perhaps there's some density in the middle, which would be a criterion for safe construction. And that is what they set about exploring with a bunch of shear box tests. And what they discovered was if you had a dense sand, it dilates and you get a very strong stress strain curve. If you have a loose sand, it's a very soft stress strain curve. If you plotted it in terms of void ratio, the dense one would dilate, the loose one would contract, but it all went to the same void ratio in the end. And they called that the critical void ratio because that was viewed as the critical construction condition, or that was our target, our critical target we had to compact to. And that was the origin of critical state soil mechanics. It was as a very simple go, no-go criterion for compaction of fill. And I should say magically, this critical void ratio was found to depend on confining stress. Now, this critical void ratio turned out to be unique. Didn't matter where you started loose or dense, you got to the same critical void ratio. So that when we started saying, well, how should we apply mathematics to the behavior of soil? And you can see this diagram, the guys who did the work originally, this is Casagrande and Taylor, they've labeled the diagram A, B, and C. So that was their thinking was you measured some stress strain behavior and magically you got some volumetric changes, and then magically it all wound up in a common endpoint. Well, what we do in critical state theory is we actually say this diagram is back to front. What we want to do is take that as a reference condition. And that reference condition is then tells us, okay, this is where our end state is going to be. And if we define a deviation measure from the end state, which is simply the difference in void ratio between the critical void ratio and where we currently are, and that's the state parameter, which is this symbol, Greek symbol here, psi, then the idea is simply that psi goes to 0 as distortional strain goes to infinity. So we now have a mathematical idea around this pragmatic engineering feature. And what we then say, we can work with this mathematical idea, and we can now predict the stress strain behavior. So rather than doing a bunch of tests and saying these tests have some sort of magical property, we can say, actually, no, we can do the physics and we can go the other way around, and we will predict the stress strain behavior from a void ratio difference. And of course, the reason we like doing this mathematically is if you know your end condition, which is this thing here, then the mathematics become rather well controlled. I have to introduce you to one further idea before I give you the complete framework. And the further idea is this: it's the soil strength comprises a couple of components. If you think of a shear box here, and I'm sure all of you have done some shear box testing in your early days of studying geotechnical engineering. So there's our shear box in here. When you push sideways on the sample, if it's a dense sand, it dilates. And you can see the weight on the hanger, which gives you a confining load. You can see that weight rising up. Well, clearly you're doing work to lift a weight. So the idea is the guys had, and this was Taylor and Bishop, they said, well, soil strength has got to be regarded as two components. We have what they call true friction, which is what I've indicated here in green. And then we have what in those days they called interlocking, was the idea of how the particles had difficulty in moving over each other. Today we call that dilatancy, but the idea was that the rate of volume change as you deform the soil actually did work, and that work needed to be added in. So in those days, for a shear box, they wrote these ideas as tau over sigma n, or mobilized friction ratio is the rate of change of volume with displacement plus the true friction. And today we would write it in this form here, where you do it in general 3D stress spaces. That's the Greek letter eta. And we use the dilatancy, which is the volumetric strain over the distortional strain rather than this, and M is our critical friction ratio. So this idea is called stress dilatancy. And I should say here, there are variations on the theme. There are different idealizations you can have, but they're all operationally very similar. And this is the equation I prefer, which we work with. So how do we pull it all together? Right, this is how we pull it all together. And there's a lot on this slide. I'm going to take you through it slowly. On the left-hand side, I have got a QP plot. You're well used to plotting stress path if you plot them in QP space. This dark blue line is the current yield surface for whatever the current void ratio is. And that means if the stress state lies in here and you make a change of stress, you'll only get elastic strains. The moment you touch the yield surface, all of a sudden you get plastic strains. Now, I've actually put two graphs on top of each other because you notice my axes here. I'm plotting distortional strain increment and plastic volumetric strain on the same axis. So this is, if you will, two graphs put on top of each other. And you don't get a free choice in what these groups of stresses and strains should be. They have to be what's called work conjugate. So the product of this times that plus that times that is the amount of work going into the soil. If you use these work conjugate choices, then there is a theorem. I don't mean a theory, I mean a mathematical theorem that the strain increment vector, which is the ratio that to that, has to be perpendicular to the yield surface. And the yield surface has a shape chosen so that wherever you go on that yield surface, dP, the latency, is m minus eta. So we've just reversed our stress to latency law now. So for whatever stress state we have a soil property m, and that tells me what my dilatancy will be, which is where my strains are going. Now, we always use the same shape of yield surface. If you have a yield surface that always has the same shape, even as it changes size, you only need one parameter to describe the yield surface. So what we do is pick this point here, which are shown in orange, and we use that stress as a scaling of the yield surface. Now, where does the critical state come into this? This green line is, if you will, a phi CV line. That's our soil property M, our friction ratio, and the critical state lies on that line. Now, what we do is we link what we're seeing in essentially a triaxial situation over here, or a stress strain test, with void ratio, which is on the right. So on the right, I've got an E log P plot, and my green line is my critical state locus. Now, if I'm at this current void ratio here, just say, then the stress for that void ratio in the critical state is this green dot here. And that stress is in the critical state. This is a line of the critical state. So that gives me the stress measure of where this point is. So I've now linked void ratio to my end condition. And how do we proceed? Well, it's very simple. The basic idea is that, and this comes back to, remember I told you the state parameter has to go to 0 as strain goes to infinity. So as you put on distortion or shear it, orange dot has to move to green dot. And that's a hardening law. It's as simple as that. And there's another little condition that you do some mathematics around that. You in fact find there's a limiting strain rate, so or limiting the latency. So there's a limit on how fast it can move. So this all looks terribly complicated, but I guess what I'd like you to get in your perhaps fix in your brain or in your thinking, in essence, what we're doing over here is looking at what you observe in a triaxial test. And this is almost what you observe in an odometer test. And we're putting it together a mathematical framework to say, well, actually, soil doesn't know whether it's being tested in an odometer or a triaxial. So the two behaviors need to be pulled together. And when we pull it together, we've now linked void ratio to strength. And that's the intent and the purpose and the offer of critical state soil mechanics. So what does it look like? Well, these are the equations that give you the behaviors I've just described. And there's nothing worse than looking at equations on a screen. So I don't particularly expect you to look at these equations and study them and write them down or anything like that. But what I'd like you to observe is the equations are very simple. And there's three of them. And remember I told you that all plasticity theory always has a flow rule, a yield surface, and a hardening law, although that's what these equations cover. On the right, I've put some names who are associated with the development of these particular equations. And we didn't get them all developed at the same time, as is the nature of things, where as understanding of material behavior goes on, somebody observes something and somebody else then builds on it. So the first observations were 70 years ago, then 50 years ago, we turned it into a yield surface, then the hardening law got, well, the first ideas about the hardening law were 70 years ago, but it wasn't until formalized mathematically till 30 years ago. But those are very simple equations. And if there's any catch, they have to be solved simultaneously. And you can't substitute one into the other to get some simple stress strain curve. In essence, plasticity theory tells you the current stiffness. It doesn't tell you the current strength. So you have to integrate along the path. And I'm going to show you that in a second. Any proper theory should have properties that are easily understood, and understood by just looking at test data or plotting up test data on some graph paper. It shouldn't require some magical explanation. The properties involved, and by the way, properties should be independent of void ratio and they should be independent of stress level. They're supposed to be dimensionless numbers that in principle you can determine on reconstituted samples. So these are the properties. I'll just describe them and then I'll show you them when I run you through the calibration. This here is gamma. That's the altitude or height of the critical state in the log P plot, and by convention it's defined at 1 kPa. Lambda 10 is the slope of the critical state locus. The subscript 10 is to indicate it's on a base 10 logarithm. We do that because when we do the mathematics, we are actually incrementally integrating. So we often work with exponentials and natural logs. So, but nobody in the lab wants to report data on natural log scale. So we're all familiar with reporting on base 10 graph paper. So we subscript it by 10 to clarify that that is the logarithmic base used to give the numerical value. And there's just a simple factor of 2.3 between them, which I show on the slide. M is the critical stress ratio, and this is the same idea as phi CV or phi C, call it what you will. This is the friction ratio in the critical state. There are two other properties which and you're probably all familiar with those things I've told you, if any of you have dabbled with critical state. The two other properties come along. We actually find that there's some volumetric plastic work. And Nova came up with a simple representation of that, and I'll show you that in a moment. And that is given the property N. And then there's a limiting dilatancy, and that's not X. The convention is properties in critical state theory should be uppercase Greek. For some reason, they violated it, and that one became a lowercase Greek lambda. But all these others are supposed to be Greek. So that one, it looks like an X, but it's actually the Greek letter C, which is chi. So that's the parameter there, and that controls the limiting dilatancy. And again, I will show you some data to illustrate how they work. And then there's a plastic hardening modulus, which is roughly the equivalent of Young's modulus, if you will. It's very closely rated to lambda. As you get more compressible, the soil gets less stiff in shear. I'll show you the role of that parameter. So let me get on and show you some data. And particularly going back to Tar Island, we have 4 of the sands in the Alberta oil field, or the oil sands, that have been tested for the critical state. And this is the critical state locus determined on those sands. This is from different labs and slightly different sites, broadly geologically the same sand, slight difference in fines content from one to another. This lambda 10 is simply the slope of those lines on a semi-log basis. You'll find sometimes you'll get a slight deviation from a semi-log behavior, but for the purposes of what we're doing now, that's a modeling detail. And here we didn't have enough data to define anything better than a semi-log line, so we use the semi-log line as our case. The property gamma, by the way, if you project this graph across to 1 kPa, gamma is just the void ratio intercept at 1 kPa. So that's 2 of your properties. If I go on, I should mention this. This is looking at this lambda 10 versus fines content, just as a quick indicator. And I've got a whole bunch of other soils we've tested over here. And what we find with these oil sand tailings, they're broadly similar to other soils. There's nothing magical about them. They're mid-pack, shall I say. Okay, let's get onto this parameter N and M. If you plot the maximum strength, and you plot it rather than plotting mobilize, phi peak, we actually have to do is stress ratio. I know in geotechnical engineering, there's a tradition of using angles for everything. In applied mechanics, we don't use angles, we use stress ratios. So eta max is simply the maximum value of Q over P. It's a mathematical transform of mobilized phi, but we work with stress ratios. If at that maximum strength, you plot the maximum dilatancy, and in fact, because we have a compression positive convention for soil mechanics, maximum dilatancy is mathematically d min. So this is the dilatancy at peak strength. If you plot that versus strength, you get a straight line. And the intercept of the straight line with the 0 dilatancy axis, that is your critical friction ratio, MTC. And you can see here it's sort of something like 1.28 for our oil sands. This is oil sand data, I should have said. And the slope of the line, if you have the Taylor-Bishop idealization as they first developed it, that line would have a slope of 1. And you always find it's less than 1. Well, not always. Most of the time it is less than 1. And Nova said the reason is because some of the work is actually going to volumetric strains. And he said the proportion of work going to volumetric strains is his parameter N. So that leaves 1 minus N going into shear, and that's what we see here. So that the grade, that's why we have this 1 minus N as the slope of the line rather than calling it N. Some people are now calling that N star, as N star equals 1 minus N, just to make life easy. But anyway, that's all it is. It's a slope of a strength plot. The last thing we've got to do in terms of pulling up properties is we have to relate properties to void ratio. or latency to void ratio. And mathematically, you expect that d min is a linear function of state parameter, and it's not the initial state parameter. If you look at some of the stuff that's been written in literature, including some of the stuff I first wrote, we're using the state parameter at the start of a traxial test. It was convenient, or convenient in the lab, convenient for plotting data, but it's actually not appropriate mathematically for when you start pulling stress strain behavior together. You need to work with a current value. So this becomes the state parameter at the maximum or minimum latency, and you get a straight line. And the property chi is simply the gradient of that line. And that's all we've done with the lab test. And we now have more or less a complete set of properties for our soils. And here I've just tabulated on the screen the values we've got from the various sands we've tested over the years. Some of this early data, they focused on undrained tests, and we didn't get the data we need to pull off N and chi. So what we've done for Tower Island, we said, actually, this parameter set here is not a bad representation. As you see, it actually matches quite nicely, and that's the one we went with. How well does it work? Well, here's a test on Mildred sand. This is a very dense triaxial test, and the brown is what's measured in the lab. And you can see the lab test has a bit of glitch around 12% strain. The blue is our theory. And it's rather beautiful fit, I think you'll agree. The parameter H, which I hadn't introduced to you, is in effect is defined mathematically slightly different, but you can think of it as the initial stiffness in a triaxial test, an initial tangent stiffness when you start loading. That's parameter H. How well does it work in loose? There's the fit to loose. You know, everything is really capturing the behavior of our soils, really quite remarkable accuracy. And we're doing it with very, very few parameters. Okay. We also, I haven't talked to you about elasticity, but we actually have to include elastic stiffness in what we do. And over the more recent years, the last 20 years, or perhaps the last 10 years, there's been a lot of seismic cone testing to pick up Gmax. And what here I'm plotting up is the results of Gmax from a particular campaign of seismic cone work on Tower Islands. This is actually at a higher part of the site we're looking at. And we have really three types of
Todavía falta una hora más que termine. No puedo.
Sorry. I'm so sorry. Wait a minute, please.
Yeah.
Okay.
Can I continue?
Yes, please.
Okay.
Sorry.
Apart from the interruption from his daughter. No worries. Okay. We have three types of placement. We actually have compacted tailings in the upstream raise itself, which is the square green dots. And as you might expect, they got quite high modulus. The yellow diamonds are beach above water, which gets a certain amount of drying. You get a little bit better density. So they have their Gmax sits in this range. And then we have our beach below water, which is our loose tailings. And that's data on beach below water. I've thrown on a couple of guidelines for a standard quartz sand, which is dense or loose. And you can see it's behaving much as you would expect. For this analysis I'm going to show you, our base case, we actually put this heavy line as what we took as our Gmax versus confining stress idealization. And the reason we did that is I've spent a bunch of time with subboard pressure meters, and we tend to find that the mechanical modulus is a little less than the geophysical modulus. So just as an engineering judgment, I said, well, okay, for this analysis, which involves large mechanical deformations, I want to come with a low bound to the seismic measurement. So that became our base case idealization. And this is the fit. Having gone through all that process, the pink line is one of the stress strain curves from a liquefying test, which you can see an undrained triaxial test from 1975. This is one of the original tests of the guys who observed the slump as part of their learning how to build a dam. The blue line is our calibration procedures. That's our prediction of their pink line based on what we've got. So I said, actually, that's pretty good. I'm happy. We'll proceed. We think we have a working calibration and a good understanding of the behavior of this material. Now, everything I've presented you so far is what I would call a laboratory discussion. We always know what the void ratio is. Well, assume we measure it, we know what the void ratio is in any of our lab tests. That's not the case we have in situ. You know, in practical terms, as you all know, we use the cone penetration test to assess the void ratio of the ground, or in our case, we're interested in the state parameter. And there is a theoretical relationship, which is Q, which is our normalized tip resistance, which is QT minus P naught over the effective P naught, is simple exponential relation of the state parameter. And we'll, of course, use that equation upside down to get the state parameter from the measured tip resistance. What I want you to observe here as we go forward is that I'm sure you're all familiar with the NCER method for earthquake liquefaction things. Well, in contrast to their methodology, when we're doing critical state soil approach, there is no fines content correction at all. In essence, what they're doing with fines content is a very poor approximation of lambda. But since we've measured lambda, and we know what the compressibility is, we don't use or any way involve fines content corrections. Also notice we don't use a reference pressure normalization. You'll find across all the NCR things, they're doing QT1Ns and all that kind of thing. We're doing a mechanics. So everything is a simple stress ratio. So we operate with Q and we have this simple equation. So how do we, let me show you some CPT data on the site next. This is one of the soundings working on the beach above water upstream of a cell and then pushing down into beach below water. And of course, you have to start on beach above water because you can't put a drill rig out on beach below water because it sinks. So, and what you can observe is, you know, quite a fluctuation in tip resistance. If you look at the pore pressure profile over here, it's essentially a drain sounding. And these spikes in here are residual bitumen. Sometimes the treatment or the process plant doesn't work perfectly, and we get some bitumen entrained in the tailings in a particular layer. So when you see that, that's a spike caused by bitumen. This is looking at the overall cross section we're analyzing. Now, top right, I've got the sketch from the original paper describing what was going on. And they made quite a clear distinction between beach below water material and previously overboarded of what we now call beach above water sand. So we went looking through the more recent campaigns of CPT testing, and there's been a lot of testing done in that 10 years ago to identify a section which sort of matched what these guys reported. So this pink line here from their sketch of 1975, we said, okay, we look at all these CPT data, and I've got, I should say, 1, 2, 3, 4 CPTs on the screen. And these have been stacked by elevation. So we went looking through these CPTs to say, okay, yeah, I could just about buy a beach in here. So perhaps these 4 CPTs are a reasonable representation. This here, I should have told you, is the current beach above water, and it then goes off into the pond. This is the upstream raise that's been placed. So we've got an upstream raise here, which is sitting on previous beach below water, or and this over here and extending downstream is compacted cell, and that's our going off to the right is our upstream constructed dam with tailings obviously below the upstream construction. The blue is the water table, and because we've got engineered drainage measures in the dike or in the dam, the water table drops as you come downstream. So the region of interest for us for our analysis of representing things is in here, and I've given you the spacings of the CPT at the top. Okay, I'll give you a photo. This is a photo from the day when they were, this is back from 1978-ish, not quite 1975. It shows you how they were doing things. What they would do is they would put a, raise some small size to with a dozer, and then they would discharge the tailings, and they put a weir over here, and the sands would drop out, and the residual tailings would run across there. So that was how they developed their cells for arrays over quite a distance. You can see over here a discharge then into current deposition at beach of water, and there's the tailings pond over here. What I'd like you to notice is this isn't quite the regular simple pink line that they have on their actual cross section. We'll come to that. But that's what it looked like at the time on the deposition. I'm sure you've seen similar in other tailings impoundments. Now we're going to look at the CPT. So how do we get the state parameter from the CPT? Well, the way we get, it's not just a state parameter. The way as a profession or as a geotechnical engineers, we get void ratio, relative density or state parameter from the CPT in sands, by and large looks to calibration chamber testing. And that's what you have here on the left-hand slide. That is a large tank of sand. It's 1.4 meters diameter and 1.2 meters high. And the guys have placed sand in there in layers carefully to a uniform density, or as best they could achieve a uniform density. This tank is lined with a rubber membrane and a rubber membrane at the top, and we can then inject or pressurize that membrane using water, much like a triaxial test. In fact, you can think of this as a large triaxial test. And we can bring the sand to a particular stress state. And it doesn't have to be the same horizontally as vertically. We can have anisotropic stress states. And then we push a standard CPT into the tank through a hole in the top. And we record the data. And we can pick off from the trace a typical tip resistance for the from the CPT going to the tank. And these dots here represent a result. And so, for example, if I've got a confining stress, say, of whatever, about 80 kPa, and I've got a sand of this density, I measured whatever it is, 25 megapascals. These numbers on here is we can take the void ratio of the tank, and we have done triaxial testing to define the critical state locus of that sand. And we can then say, well, we know the critical state locus, and we know the P dash, and we know the void ratio. We can actually calculate the state parameter. And for sake of simplicity, we've left off the minus sign. So that 0.21 means that test had a state parameter of minus 0.21. And you can see there's a very nice set of radial lines. Well, if you take gradient of a radial line, it's this magic ratio Q. It's just Q over P. And if you turn that same data and you plot it in Q over P, you get our lovely, simple exponential relationship. Now, there's a small trouble with this. And when we first got involved doing this, the hope was that we would more or less get the same line with every sand and every soil. And the answer is that's far from the truth. What we're measuring with the CPT is not a property of the sand, we're measuring a response. And that response depends very much on its compressibility, on its shear strength, on its dilatancy parameters. So this line, you can't do a line on sand A and expect it to apply to sand B. So we need to do something to generalize the framework. And so what we did is, and the way this is usually done, is we look to what's called cavity expansion theory. Now, what is a battleship, which is your photograph you see on the top left, doing in a talk about soil behavior? Well, the answer to that is, as in virtually all modern technological developments at the frontier, it's the military that drives big budgets. It's the military requirements that tend to lead to the largest scientific advances. The battleship you're looking at there is 100 years old. And in the battleships, well, like you see here, the shell that gun would fire would weigh about a ton, and the shell would be accelerated from at rest to something in excess of Mach 3 in a distance of 15 meters. To do that requires quite enormous pressures, and what they found was that gun barrel deformation became a major topic of research, shall I say, to various navies. And that's the origin of plasticity theory. It was actually to understand deformation of gun barrels. And the reason it's called cavity expansion is the cavity was actually the gun barrel. It was a cylindrical cavity. Now, why do we like cavities? Well, the answer is it makes the mathematics very simple because, yes, it's a 3D problem, but we can write everything in terms of radius. So even though it looks 3D, mathematically, it's actually 1D. And the nice thing about cavity expansion is that if you increase the cavity pressure, so you imagine we've got a small cavity here and we start increasing its pressure, and eventually the cavity, we increase the pressure and the cavity expands because we expand it out here. What you find is you get a pressure versus displacement diagram that looks like this. And at some point you come to a limit pressure. And you get a limit pressure because as the cavity expands, the area of the cavity is increasing because of the circumference is increasing. So for any pressure, the load is increasing. But equally, the amount of ground or steel you're acting against is also increasing. And it gets to a point where the processes come into balance. And that gives you what's called a limit pressure. And the idea was then suggested during World War II that this limit pressure, which we knew about from gun barrels, could actually be applied to metal forming. So when we were trying to produce better machinery during World War II, we started looking more scientifically at metal forming processes. So they had the idea that this limit pressure, which could easily be done by a punch indentation test on the metal, would tell you how the metal would deform when you're fabricating it. After the war, this idea was picked up in soil mechanics, and it's used today as the basis of pile design. Notice on my diagram on the right, it says pile. I've scanned this out of a paper. And the idea is that this limit pressure corresponds to the pressure acting on the base of a pile, or in our case, the base of the CPT. Now, it's not quite perfect because actually we have friction in here, and friction on the side is absent in this calculation. We also have friction down here because that's a rough piece of steel pushing into the ground. So there's actually more loads and stresses in the system than in the cavity expansion. So this is an analog of what we're doing with the CPT. And what we find is that tip resistance has a scaling factor on the limit pressure. So how do we establish the limit pressure? Well, very simply, we do a mathematical cavity expansion in sand. And this is using critical state theory, and we compute this. And we then look at the relevant chamber testing, and the ratio of the trend line through the chamber testing to what we've got with our mathematics is our parameter CQ. Nice and easy. But the beauty of having done this now, though, is we have a methodology we can apply to soils of different properties. And I should say, what we found is that these K&Ms are actually function of the elastic rigidity. IR is simply G max over sigma V. And we found that systematically K and M depend on HM, chi, lambda, etc. So we have ourselves a nice framework which we can apply to any soil. Of course, if you're of cynical disposition, you say, this is a very nice story, Mike. How well does it work? Well, what I have put on the front of the screen in front of you is 331 calibration chamber tests. The bottom is supposed to be truth. We've got a calibration chamber test. The various investigators, and you can see there's not just one university, there are a whole bunch of people involved. And they've reported that this test was done at a particular void ratio and a particular confining stress. What we did, we got samples of their sand. We determined the CSLs. We could convert their reported initial conditions to a state parameter. So I've called that truth. That's a state parameter based on what the various labs have reported with the standard calibration procedures. they've then done this test and they've reported a QT value for that EP0 pair. So we've said, okay, for that particular sand, we know what its properties are. We will take it through this finite element procedure if I showed you, calculate out the K and M values, and then from their reported QT, we can calculate out what the apparent state parameter is. And that is the cross plot. The line down the middle is the one-to-one equivalence line. And see if I've got the numbers on it. Yeah, 80% of the data lies plus or minus 0.04 of the calculation. Now you might say, well, that's a fair bit of scatter. I think most of the scatter is actually caused by calling it testing error is a little harsh, although technically that's correct. The problem is these tank tests involve 1.5 to 2 tons of sand. And we cannot measure void ratio that accurately, or at least vary a bit from place to place. And also there's a certain amount of judgment. When you push a CPT into a tank, you can see the effect of top caps and bottom caps, and you have to make a bit of judgment, what is the representative value? To illustrate the effects of these things, I've highlighted 2 tests here from the Ticino data set. That's test E139, and I can't see off the screen what that one is. Hang on a second, so I get rid of, no, I've got, my screen's cluttered. Anyway, that's the second test. And the point of these 2 tests is they have reported identical void ratio and confining stress to about 3 significant figures. Yet the reported tip resistance varies by a factor of 2. So I think a lot of the scatter is actually reflecting testing precision in chamber testing. And the important thing to us was that our trend line was unbiased. There's equally amount of stuff above and low, and we're on a one-to-one plot. So I very much like this procedure, and it gives us what are my coefficients to compute the state parameter. So this is how it's interesting to say, because these calibration chambers have their own troubles and things like boundary corrections and things like that. And we had an opportunity in a recent dam failure to check our calibration, our procedures in the field. What you're looking at on the photo on the left, this is Cadia. This is the Cadia liquefaction slump. And what I've highlighted in blue is that a year before the slump, they put down a CPT, and in that location, which turned out to be more or less in the center of the slump. And not only did they do that, they did a bunch of fixed piston sampling with a particular sample, which reportedly produced very high quality samples. Now, when the Board of Investigation into the slump was put together, we were not aware of this piston sample testing. And we predicted the state parameter profile using the methodology I've shown you for the tailings, which is shown here in these green dots. We then discovered that the engineer of record had done this piston sampling, and we discovered a memo from them to the owner, and bless them, they had actually measured the density or the void ratio of the recovered piston samples in the field. Now, these tailings were a little bit stratified, so we were not entirely sure what was in the tube. But it broadly, there was a predominant silty tailings and the slightly sandier one. So we actually determined the CSL for the predominant tailings, which is the purple dot, and for the sandier tailings, which is the orange dot. And truth has to lie between those 2 points. And we didn't know whether the tube was full of sand or full of predominant material, but we said, okay, we'll just draw the band. And you can see we've got 6 of these, and it really beautifully straddles our prediction. We can only call it a Class B validation because we were not aware that the reference data existed, but it did exist before we did the prediction. So it's only a Class B one. But that made us pretty confident, or added further confidence to that previous cross plot I showed you. We have got a pretty good handling of what's going on. And we actually had calibration chamber testing for the Alberta tar sands. And so this is the chamber I've shown you before, same chamber. And we ran the numerical procedures against that. And the trend line we went with was the numerical procedure. We did that because what we've done here on this graph is this pair here there's the physical test, and that's what I've calculated for with my numerical procedure for the state parameter, and that's what we got with the physical test. But I prefer, because our finite element procedures have been calibrated against a wide database, and because chamber testing has quite a high standard deviation, I said, okay, for this exercise and understand this liquefaction event, we're going to go with the trend line from the numerical methods, and it's good enough, it's close enough. You know, the such physical tests as we have are consistent, so that's what we went with. So back to our cross section here. This is our CPT as I've introduced you to, and what we're going to now do is process these CPTs with the methodology I've described. And we do that, and we get this pattern here of state parameter versus depth, and you can see there's a lot of variability. What are we going to do about that? Well, how we deal with variability is this way. I've got to take you to the Netherlands. This is the Oosterschelde barrier, which is to protect the Netherlands or the Scheldt estuary from North Sea tidal surges. And it was built on, these are concrete caissons, and they're founded on loose sand. And storm surges involve wave action, and the waves produce cyclic loading on the barrier. So fairly comprehensive testing was undertaken in the 1970s, and that involved centrifuge testing because it was finite elements were in their infancy at that time. And what they did, they did centrifuge tests with uniform sand pads, but then they said, well, we know the sand's not uniform, so let's try looking at it. So what they started doing was taking their centrifuge model, and they'd scoop out little teaspoons and put in loose sand, and they did different proportions of loose sand. And what they found was that it seemed to be the loosest 10% of the sand that actually controlled how the caisson behaved in a centrifuge. So that's your first point of reference. The next point of reference is this one here. I've gone from the Netherlands. We're now up in the Arctic, in the Canadian Arctic, and this is about 75 kilometers off the northern Canadian coastline, and it's in the Arctic. The sea is frozen for 9 months of the year in this location. And not only is it frozen, the ice actually moves. So what you're looking here is this ice sheet is moving past the structure at about 1 knot at the moment. This ice here in this picture is only about 0.6 of a meter thick. The thickest we crushed continuously was 3.5 meters. For reference, that is about 100 meters across. And this is an oil exploration platform. That's how we did the oil exploration in the Arctic. Now, when the ice crushes, it produces quite large vibratory loads on the platform. And how do we keep the platform in place? Well, it's actually, even though it looks very impressive, it's a giant shear box. To resist these ice loads, we actually put a lot of weight into the structure. And we did the weight by just using sand rather than concrete, because this, in fact, is an exploration platform, so we have to move it from year to year. And if you do it with concrete, you're never going to move it. And it also sits on sand as well. So this is, in a way, well, actually use much of the technology developed for the Oosterschelde barrier. We use the same dredges, the same sand placement techniques, and so forth. But of course, we have moved on a bit now, and we've got a lot of CPTs because we're now in well, the Osterschelde was sort of 1970s. We were in the 1980s. And it was mentioned in the introduction, my book here. That book, 80% of the book comes from the engineering for this platform. That's where all the testing was done, all the investigation. And I was the engineer of record for this platform deployment. Now, I'm sitting there and I've been educated by Alan Bishop about the way loose sands behave or don't behave. And I'm well aware we have cyclic loading. So you better believe I'm one concerned engineer. So we did a lot of CPT testing to understand what our sand was like. And so the picture you're seeing here, notice here we've got a deck. Well, that's actually a box girder deck with storage and offices in it. But underneath it, there's an air gap. And this is the air gap. So that's the underside of the box girder deck. And that is a sand surface that you can't quite see. And this is where we're doing some CPT testing. We did a lot of it. And if you look at it in plan, this is the inside of the structure. That's about 72 meters across from there to there. Those green dots are a CPT. The orange dots are a self-bored pressure meter profile. And the green, or so the yellow thing in the middle, that's the location of the oil, where the oil wells went down. So we were doing a lot of testing. And what we can do with that testing, you can start seeing loose pockets and dense pockets. And we had to bring in the test quite close to each other before we began to start seeing the pattern. So you're looking here at 6 CPTs in a line. If I back up, can I back up? No, escape out of that. Yeah, we're looking down. I think it's this line here we're looking down. Those CPTs are 9 meters apart. And you can see here the hint of a dense layer, and that layer goes over there, it comes over here. We're pretty well lost it over here, and we're pretty well lost it over there. Down here, you can see a loose layer, and it continues. Well, what you can do is you can take that sort of body of intensity of testing, and you can work out standard deviations, and you work out means, and you can work out a trend of a mean. And you can then go to a computer, and that's what's called geostatistical modeling. You can use a random number generator to create images of what your ground conditions might be like. And that's what you see at the top of the slide here. That is computer generated, and the light gray is the looser ground, the dark black is the denser layering, and you can see the structure. Now, we don't know what goes on between the CPTs. We only have a statistical description. So what we do in this situation is we roll a dice in the computer and say, okay, let's roll the dice for this pattern of CPTs, and let's populate the entire box, as it were, or the finite element analysis, populate each element with a void ratio such that the pattern of void ratio matches the pattern we would get with the cone penetration test. And what you're looking at here is 6 what we call realizations. So here we've rolled the dice once, rolled the dice again, rolled the dice again. And what we've then done is we've run a standard earthquake against them with a cyclic liquefaction model. And here, what you see in here is the color coding is shown on there. That's the RU value. So when we put the standard liquefaction test here, we get this much pore pressure. Over here with this realization, we get a lot more liquefaction or a lot more pore pressures, and it varies from roll of the dice to roll of the dice. Anyway, that's the pattern we get representing the detail we see with the CPT. Now, for an engineering calculation, we use what's called a characteristic value. We make the whole domain one state parameter or one void ratio, one relative density. So what we then did, we said, okay, if we use an average and we run our standard earthquake for it, we actually predict no excess pore pressure at all. If we use the 50 percentile, we get just a hint. The 60 percentile, which I mean is 40% of the ground is looser than what we measured with the CPT, and the 80 percentile means, 60% is denser than what we measured with the CPT, 70% is denser, 80% is denser, and the rest of it's all. So what we're seeing here is something like the loosest, you've got to compare this stuff here with the stuff here, and you say which best captures the pattern we've got above. Well, clearly this one, which would be the loosest 30% controlling with 70% being denser, that is inadequate compared to those. Quite clearly here on the 90%, I would say this is back to the Osterschelde idea that loosest 10% controls. That's too pessimistic. So our rule of thumb was something like the 80 percentile was a pretty reasonable engineering view for what would control stochastically. So we go back to my Tower Island case. Here is our process CPT data. And these lines on here are now the engineering judgment of what is characteristic. Now you could go and start doing statistical games and try and work out formally what percentiles were and plotting them up. But in all honesty, I prefer to do it by eye, because the eye is not so bad once you're looking in. And this was the characterization we came up with. And you can see, we've allowed one or two bits a little bit looser than we think. By the way, I should say dense is over the left, loose is over on the right. So we're honoring that, and clearly down here, which is much looser ground, there's a harder layer in here, and there's a layer down the bottom. So that's what we came up with. That's how we did our characterization. We've also got to come up with K0, because when we use finite element analysis, you've got to tell it what the starting stresses are. And we have actually done self-bore pressure meter testing in these tar sands, and that's a self-bore pressure meter there. What we do is you expand it, you can measure a the stress or pressure displacement curve, and you can mathematically model that, and you can get K0 out of that, because the expansion depends on the stress in the ground. And this is the plot for Tower Island. Muscat, yeah. And up here we are in, so we're plotting horizontal stress versus vertical effective stress. And up here, we're in where the dikes are. This is compacted ground. And surprise, surprise, the stress state is quite a lot higher than in loose tailings. If we looked at the stuff that we felt hadn't had any compaction effects and any wetting or drying, we came up with a K0 of 0.6. These over here were quite clearly disturbed tests. That's just data we threw away as when you looked at stress strain curve, you said, oh, this is hopeless. The test is disturbed. So we said, okay, we're going to run with a K0 of 0.6. That's what we adopted. So this is what our model for Tower Island looked like. We had our layer of, which is the one the guys said should have existed in our idealization. We say based on the CPTs, it's not there's a material above it and material below. This is beach below water there. This is relic beach above water, and this is beach below water. And you're going to see this is our upstream raise that they constructed, and the failure comes when the purple reaches its top. We found it difficult. They said they were building on beach below water. I don't know how you would do that, because you put a bulldozer on beach below water, the bulldozer sinks. So we said we believe they actually had to place, even though they said they were going directly on beach below water, we think they must have placed a sand pad. That's how we've done tailings ones I've been involved with. You get a sand pad out, and then you can get a low pressure bulldozer out there. So we actually modeled a sand pad in. We also put a weak layer in here. I'll explain why we did that in a moment. When the guys from 1975 wrote their paper, they discussed the stress paths of this point A. But we said, well, never mind point A, let's actually look what's going on in point B and looking at point C. So we took 3 marker points for our analysis to see what was going on. And we then also came up with, even though I've talked to you about a base case, and we said there's some issues. I've emphasized that they said that there was this very clear marker layer, which is the pink layer, which is the transition from beach above water to beach below water. When we look at the air photos of the day, it's very difficult to believe what they showed was correct or the best representation of reality. So the base case, we are actually taking and honoring everything they reported from 75 as best we can. scenario number one, we said, actually, if we look at the photos, we don't actually quite agree with what they said was the thing. So we said this hard layer was simply not present. It's so discontinuous, effectively it doesn't control the behavior of the rays. There was a further scenarios we're concerned with, you know, if you're not careful as an engineer, you talk yourself into being conservative and conservative and conservative, and you wind up, you pile conservatism upon conservatism, and that doesn't really help with the case history. With a case history, you really do need to go with best estimates so we're saying perhaps our procedures have a conservative bias in them. So we said, let's go with something a little bit better. So that became the denser thing. We also said, let's consider the beach below water layer was thicker. Perhaps what we've done from the 2012 CPTs, which only suggested about a 2 meter thick layer, maybe back in 1975, the guys were telling the truth and it was thicker. So we made it 5 meter thick, just to see what the effect would be. And the other thing we explored was that, you know, I indicated my concern about, or experience of what we see mechanically is lesser than what we see geophysically. So what we explored with scenario number 4 was, let's put that idea in play, and we used a reduced Gmax. There were no piezometers in this case history. You know, these were very pragmatic engineers. Liquefaction was extraordinarily new, and they were doing everything on a fairly simple observational basis. But when we look at the rate of rise they're going at, and we look at the diffusion or the dissipation time of it, they should easily have been in the drain situation. So we do indeed believe there was no excess pore pressures. You just look at the CV values and the rate at which they were going, it has to be drained. So we modeled it drained, and we then tested for a perturbation, as I'll show you. So now what you're going to see, I'm going to show you the results of the base case scenario. What you're going to see when I press the go button is you're going to see the fill being placed. Okay, and then at the last moment we will test it, and this all happens drained, and you'll see color contours which shows the ratio of eta over m, which is the mobilized stress ratio normalized by the frictional strength. When eta over m hits 1, you're in the critical state, and that's colored red. Okay, so let's see what we get. We're building, and we've started failing. And let's really go. Notice how it's coming down. And notice how far upstream it's gone. In fact, it keeps moving, just keeps moving slower and slower and slower. At some point, you get bored and shut the computer down. But this literally, what I'm showing you here, this was genuinely the first run of the model. And what we find with the first run of the model, having done everything as I've described at face value, not weighting anything, we get virtually a perfect match to case history. If I, oops, can run it again, just to give you a second shot at it and see it. And watch the propagation velocity. That velocity there, theoretically, is about 50 meters a second. What I would suggest to you is you go and look at the Brumadinho video, and you'll see about 50 meters a second. I think this is very, very close to what you can see in the video from the Brumadinho security camera. Okay, we'll move ahead. If we look at the onset of liquefaction, is here. What we did in the last raise, we would put it on drained up to this point, and then we'll place every load undrained, and if nothing happens, then we revert to drained and continue. So we're testing it against an instability criterion. And when we first trigger, it triggers right down here at the toe. And then, as you saw, everything develops. And what we computed when we stop, that actually is 4 meters. And we actually, even though I showed the limit here, we've actually got 500 millimeters of movement. And the guys didn't describe what their basis was for deciding how far it went. What you have here is the engineer of records thing. And what you can see is that's the shape of their surface, and that's the shape of our surface. That's because our model is hanging up. we don't have any capability at the moment in the FE method I'm familiar with of putting in a tension crack. So the reason we put in this weak layer here, we knew from the observation of the day that we think this thing moved forward, and that was basically a tension crack in there. And we couldn't do that, so we put a weak layer. But because of that, we are actually hanging up here, and we see here it doesn't hang up. If I move ahead and I actually look at my marker points A, B, and C, what we got? Well, B was the one that triggered first. You saw it triggering down there. This is the instability criteria for point B. And what you observe on that last lift, we're actually above its instability locus. So when you apply, it doesn't flip the moment you go above the instability locus. You actually need what's mathematically called a perturbation. You need some sort of a little event. They actually were using a bulldozer to move fill around. And the anecdotal record of the time is the bulldozer driver had to accelerate to full speed to get out of the way of the failure. So we believe it was a little bit of vibration from the bulldozer that kicked this thing into failure. And so B goes first. Now, when B loses strength, the load B's carrying has to be pushed somewhere else. So it goes sideways. And then what you see over on point A, yes, it's picking up load, picking up load, and then it's hit its strength. And then it dumps load. And that's a complete load shedding, and that's how the whole thing propagates. And that was the computed stress strain curve behavior on the right. In terms of mobilized stress ratios, you can see them over here, and there's a big difference. It depends on your strain history when you trigger liquefaction as to what you get. Now, if I look at the various scenarios of what we predict, the one I've just showed you was the base case, and that comes out as a smidgen over 4 meters maximum settlement, and the actual measurement, I think, was 4.8, if you go and look at the engineer records day. If we take out that layer the guys were insistent on in the day of that pink layer AA, you take that out, you slightly over predict. And of course, you can play games here and say, well, what if the state parameter was minus 0.065 rather than minus 0.06? You can get all over the place, but what is satisfying is we're very much in the ballpark just on the first case. And what I also like to point out to you is that if you're using the observational method and you're doing a raise, so here we're doing the raise, lift 1, lift 2, lift 3, etc., you will observe it's getting stiffer. So if you were measuring settlement versus raise height, you would have concluded you're getting safer because it's getting stiffer. And that's the whole problem with liquefaction. Use the observational method, you're going to get yourself in trouble. What really surprised us in these simulations was this, though. When we use Gmax at face value, or Gmax discounted by 10%, we get this, a lovely, lovely mechanism. If we reduce Gmax to a softer value, such as we might use to model lab tests, we get a simple rotational failure. Never propagates upstream, doesn't get nothing like the right amount of settlement. So Gmax seems to be terribly important to the way these things behave. And of course, you look at our liquefaction methodologies, nobody is emphasizing measure Gmax and use it as part of your analysis. Well, you can't if you're using limit equilibrium. There's no way of entering Gmax. But it's hugely important. So anyway, we're getting quite close to the end. Hopefully you're still awake. And how are we doing on time? I can't see the time, never mind. There are 3 questions that really arise out of this validation thing. And the first one is limit equilibrium valid for static liquefaction? You know, most of my colleagues, most of the consulting engineers I know always complain, why do we have to use finite element analysis? Why can't we simply use an appropriate choice of SU? The next question is, you find people say, okay, we understand this critical state theory and so forth. And if you go and talk to people like Laurie Wesley in New Zealand, they'll always say, well, you're only doing the remolded soils. Tailings is the remolded soils. It doesn't handle soils with structure. So what about residual soils? What about iron ore tailings, which are particular unusual behavior? And more worryingly, how are we going to communicate safety? You know, all these applications, when we had these boards of record looking at Cadia, Fundao, Brumbin-Mino, there's no question what the factor of safety was because it fell down. If we're going to apply these methods to an existing dam, which isn't falling down, how are you going to communicate your idea of how much reserve you've got? Because, you know, so let's look at those questions in turn. Question number one, if we're using a limit equilibrium method, we're going to be inputting SU or maybe an SU over P ratio. But SU varies with strain history, which means location. And SU, and when you look at the literature, people tend to say, well, we can get SU from, or SU over sigma V ratio from some CPT tip resistance or some processing of CPT tip resistance. But theoretically, SU depends on the kappa over lambda ratio, or the ratio of elastic to plastic stiffness. And that simply isn't in the methodology we're using at the moment. And how on earth in limit equilibrium do we deal with brittle behavior? We've known, you know, we're looking now at limit equilibrium in the context of tailings liquefaction. But we've known for a long time that limit equilibrium does not a very good job when we're dealing with stiff clay, because stiff clay also shows progressive failure, which is a form of brittle behavior. So it's not controversial to say limit equilibrium has its limits with stiff clays. So we shouldn't be that surprised to say, well, actually, what we're dealing with is beyond limit equilibrium. So my view is, if you want to argue for limit equilibrium, first off, you've got an obligation to demonstrate it works on these case histories, but you're going to spend a lot of time correcting inverted strengths, and nothing will be at face value. Whereas if we use the critical state methodology in numerical analysis, everything's at face value. As I've shown you, I've taken you through the inputs. I've done no manipulation. I've made no funny things I can't explain, and we nail it. In question two, is there other soils that critical state theory cannot represent? The answer simply is no. Now, you may need to add more detail, because if you start saying, well, structure is important, well, we need then to add structure in. What you're looking at here is, this is actually the Cadia Foundation. This is some traxel tests on the Cadia Foundation that caused the dam failure. The brown is the what's measured, and the blue is the critical state prediction. Now, how have I got that prediction? Well, I've allowed for the fact that as strain goes on, the structure of the soil gets degraded. So I've introduced a degradation model for the property M. But of course, the more detail you add, more properties you've got to put in. So you can do it, but is it worth it? Well, you decide when you're doing it, but it can do it if you need to. The final thing, really, and this is things for you all to think about, because you know, I'm retired now, but this is something you're going to have to live with. As a profession, as engineers, we've got, I don't know, something like 70 years of history in communicating dam safety in terms of factor of safety. And we've got values of these, which are deemed to be safe or acceptable in our codes of practice. But if limit equilibrium is unreliable for static liquefaction, then a factor of safety is essentially going to be meaningless. But so what are we going to do? My view is we've got to get working on building an experience base for applying numerical methods to dam safety assessments. You know, we've got these various board reports, which is a starting point. But what we need to do is the sort of thing we've done at Tar Island. The various universities and researchers need to start looking at other case histories, and we need to start describing how we might assess safety when we're dealing with brittle materials, and some idea of that. The people at Imperial College, Dave and Lydia, they've actually made a start on this, and they've got a paper in GeoTechnIA on where to go. But as a profession, geotechnical engineers, when one method has got 70 years of experience, but we know it's inadequate, clearly we've got quite a obligation to get working on some of these case histories with our new methods, which can do a better job of actually telling the regulators and society about the safety of these dams. Because right now, quite clearly, tailings dams are far outside the acceptable zone for society. Okay, before I go to questions, I'd like to bring your attention to one thing. I've taken you through quite a lot of history of soil mechanics rather than just geotechnical engineering, and quite a lot of things I've touched on. And even though some of you may have been taking notes, you'll have been swamped. And even though those of you who listen to me say, oh, I've understood every slide, you're probably all sitting back now feeling I'm fairly confused. Well, if you go and Google tar island liquefaction, title of this talk, you'll find a written paper on this case history. It's open access, means it's a free download. So please do go and download this paper and have a look through it. And that will hopefully cement it, or what I've talked about will help you grasp what's in this paper. And I hope you enjoy reading it. Okay, questions. There are 4 questions I've been sent. But before I go to those, I think I want to hand over to one of the coordinators to see how I've done, whether they want me to go to questions.
Well, Engineer Mike, thank you very much for allowing us to keep a little of all your knowledge. It was a very interesting presentation. We hope to have you in another opportunity. And also in Teams, we have more than 220 people listening to your conference. So the student and the professional community is very grateful with you. Now we are going to introduce the engineer Álvaro Pérez. He's the one who's going to proceed with the round of questions. El ingeniero Álvaro Pérez es presidente de la Asociación Peruana de Ingeniería Geotécnica. Asimismo es docente en esta casa de estudios. Bienvenido, ingeniero Álvaro.
Buenas tardes. Good afternoon, Professor Mike. Thank you for your presentation. I hope that I think there's some questions that you have predefined in your presentation. Please, if you can answer that question.
Those questions? Okay.
Thank you very much.
Yeah, I will go to screen share and I will give the 4 questions I've been sent and give you my answers. Okay, let's see where we go. Okay, question number 1 was about software. Why use Plaxis? Isn't there other software capable of performing the same procedure?
I'm sorry, Professor, your presentation, we can see, we are seeing the last slide.
Oh, it hasn't gone ahead. You can't see it?
Estoy compartiendo. Yo estoy
I think it's
Can you see it now?
Of course, yes.
Yes. So you can see the question. Yeah. Okay.
Yeah. Okay. There is it.
Yeah. Perfect. Thank you. This is the question I was sent. The first question: why use Plaxis? And of course, FLAC has been, in terms of the investigation and the failures I showed on the second slide, FLAC has been the most popular program. I think it's been used by at least 3 of the 4 boards. Now, you remember when I started out, I said with these critical state theft, well, actually all plasticity theory, we have a yield surface, a flow rule, and a hardening law. And we've got to solve those equations simultaneously. Well, there is not one mathematical procedure for doing that. There's a range of procedures we use within finite element method. Viscoplasticity, tangent stiffness, and a few more. And some of those procedures are easier to code. Some of them have better accuracy. Some of them are more stable. So the various software houses have gone down different avenues for which algorithm they use to solve the equations. if I look at the engine, and that's why it's not question of the question of package 1 versus package 2 versus package 3 is not just a question which is the cheapest, which has got the prettiest output. There's actually mathematical differences between them, even though they all are ostensibly numerical methods. If we look at engineering applications or software, we need it to be easy to use. We need to have scripts so we could, I showed you building the layers of the raises, and we need very good visual display. And it needs to be something that you use without costing too many hours to use it. If I look at FLAC, which is I believe the most popular program, it does an excellent job drained, and it actually is pretty good for scripting to capture construction details and how we build things. But when you get to the brittle failure and the undrained brittle failure, it gets seriously inaccurate. And if you look at Fundao or Cadia, we were unable to get FLAC to follow the failure down. So what I showed you in that video of Plaxis of tracking the failure, we're unable to get FLAC to do that. RS2 is another package that has implemented critical state stuff. I have no experience of that program. I cannot comment whether it does a good job or not a good job. I've not seen any of the papers based on that one. Plaxis is, when I first saw that video, it came up on Dawn's screen, I just about fell out of my chair. I have never ever seen anything like that before. But Plaxis is not as good as FLAC for scripts for constructing. Something they're working on at the moment, but it seems not as easy to use, even though it does spectacular results. If we go to research, and that by which I mean universities, then ease of use is secondary. You've got graduate students who can spend as long as necessary on the problem. And if we're in academia, we may want to look at better algorithms or more difficult situations. Imperial College, ICFS, they have their own program. It seems to do nice things, but it seems to be restricted to them. What I am seeing in universities, Abacus seems to be where a lot of universities researchers are going. Now, Abacus comes in 2 versions, implicit or explicit. From what I can see, I think explicit will probably be better than implicit, because of what we're doing involves large deformation behavior, which is what explicit is intended to do. Smith and Griffiths, they wrote a book, Programming the Finite Element Method, and there's a lot of software that accompanies that book, and it's all free. You can just download it, and it's very, very good programs. The widget, which I described for how we compute CPT calibration, that is actually a subset of the Smith and Griffiths code. It's been used, the widget uses their code as the basis of it, and we then turn it into large strain and put in a particular mesh. But you have issues when you're doing these research type things with mesh generation, and particularly plotting. So some of this research stuff is all free, but it's free to purchase, shall I say, but it's not necessarily free to use if it takes a lot of hours to use it. So for practical engineering at the moment, I believe our choices are FLAC, RS2, or Plaxis. They each seem to have their points. My personal preference at the moment is Plaxis. So I've never seen anything like that. Okay, next question I was asked was, what are the most important procedures when doing a seismic CPT? Well, that's an interesting question. The first one is to measure the groundwater pressure profile. In tailings in particular, it's rarely hydrostatic. And the problem is, if we get the groundwater pressure profile wrong or inaccurate, everything else will be wrong. It's as simple as that. So we really absolutely have to tie it down. The way we do that is it's nice to do dissipation tests during the CPT itself. Even if you're in sand, just stopping for a couple of minutes, okay, it gives you effectively an instantaneous piezometric observation, and you can then move ahead. If you're in a silt, you may want to stop for half an hour. Now, I have a colleague, he likes doing 2 CPTs, one beside each other. He does 1 CPT as a continuous push. Then he does a second CPT where he stops every meter for a dissipation test. I think that's too much. But judge it for yourself when you do it. But whatever you do, you must document the groundwater pressure profile at the time of your CPT testing. And don't forget, you can always install push-in piezometers. You know, that you might want to put a few of those in place. The second important procedure, if you look, it's not just what I've shown you today, but a lot of our methodologies are starting to use the friction ratio as an indicator of soil compressibility. That means we need accurate friction sleeve measurements, and that means we must not use a subtraction cone. So the second thing is get a compression cone. A lot of our contractors don't like it because they're more delicate and they tend to break, but cones are cheap. A dam failure is very expensive, so you need a compression cone. The second thing, which I see rarely done, is to, you know, people will what's called zero cone. You have your cone before you push it into the ground, and you push a button on the recording equipment to put everything to 0. You know, so we know it's sitting there in free air, so that we know the stresses are 0. What you should also do is, after you've done the sounding, bring the CPT out and get it into free air and see whether the values you're now measuring corresponds to values at the beginning of the test. Because if you've overstressed the cone, they won't. And if you've overstressed it, then somewhere you've gone off calibration. So just as a check. But more seriously, check calibration. There's one job I've got involved with where they went, it was an upstream raise or an increase in height from existing tailings impoundment. And they went and did some CPTs, and that became the basis of the design. And the thought came up, well, after we've done a bit of construction and raised the ground a bit, it'd be nice to see how the ground's consolidating. So let's do another campaign of CPT testing. And we discovered tip resistance is half what we previously had. We then went back a couple of years later, and then we matched the second round of testing. And we couldn't ever figure out what has gone on. My guess is somebody had input an incorrect code into the CPT. So when I started out with CPTs back in 1982, we actually took a calibration frame to the field with us, and we could take our CPT and we could check for ourselves with an independent measure that we got the thing working correctly. That's rarely done these days, but I just throw this out as, you know, it seems such a trivial thing, but do be very careful that indeed what you're measuring is what is reasonable and you haven't got some very simple slip. And the final thing I say is look at the data in the field. These days, we've all got laptop computers. We can all process there's various programs of processing and plotting CPT things that runs in your laptop. So, you know, maybe you do a day's testing and then you go home or go back to the site office. Just look at the data. Does it make sense? Does it fit your expectations? So this is not so much about the seismic aspect. This is, you know, CPT testing, things to watch out for. And these are the things I've found trip up other testing campaigns. So that's my answer to that question. If I go ahead now to the third question, have you ever heard about a dam failure in Peru? Which one? Well, the answer is on my CV, it mentioned I worked in Peru, but I only worked in constructing the Estimada tailings dam. I've not been asked to be part of any investigation of a dam failure in Peru. I do subscribe to this blog from the American Geophysical Union, because they make an effort to alert you to every dam failure, and there's one in Peru, but I don't know much about it. So that's my comment on what I know about dam failures in Peru is very little. But I'd love to be invited, but I haven't been so far. Okay, as an engineer, what has been your biggest challenge? Now, this is an interesting question, because I thought when whoever wrote this question, they were probably expecting a technical answer, and you're not going to get a technical answer. The engineering comfort zone is test charts, graphs, and equations. That is, you know, as people, that's where we started out. We went into engineering because we don't like writing essays, right? Smile, somebody. The reality is that clients, stakeholders, regulators take action, not you. And their understanding, even if they're very well educated, is basically that of a 14-year-old. So you need to be able to communicate with them to get what you believe is required to happen. And nobody reads 30-page reports. You know, the key finding sections need to be, or actions need to be in 10 pages or 12 pages. And the biggest problem for us as engineers on our university courses, we're not taught communication skills. You know, we do courses in stress analysis, we do courses in hydraulics, we do courses in structural deformations. We're not taught to communicate. So you, as you develop in your career, you need to get into self-directed learning of how to communicate, because it's a huge gap in our education. And that was the biggest thing for me. And in reality, writing and public speaking is crucial to be an effective engineer. You have to be able to stand up and explain to people why things are as they are, or why you're suggesting a particular course of action, or why something is or is not a problem. And you have to be able to do this essentially to talk effectively as if you're talking to a room of 14-year-olds. So how do you get that kind of skills? Well, in Golda, when I spent 25 years with Golda, people like going to conferences. So we had a rule that if you want to go to a conference, generally the company would approve, but you had to give a paper. And partly the paper would promote the company, but the most important thing was it would develop you as an engineer, because you'd have to get up in front of 40 or 60 people or even 200 people. And that's nerve-wracking the first time you do it. But it's crucial to do that to become a confident engineer to progress in your career. And it's also crucial to be able to write clearly. It's nice also if you can sketch clearly too. If you can make nice drawings, that's also very good. But a lot of us go into engineering because we don't like writing. You know, we liked writing, we'd have chosen a different course to become lawyers. But we need to be as effective at communications, both written and spoken, as lawyers are. And you need to develop that skill. The recommender, I spent 10 years with Gulf Oil, and Gulf Oil was very, and I think some of the mining companies do the same thing. They're very keen that their people become very good at communicating and shall I say, dealing with their colleagues and who come from different disciplines, and dealing with shareholders and things like that. And in Gulf Oil, the recommendation for the standard at which you should be able to express yourself was The Economist magazine. Because if you look at The Economist, they don't just deal with economic issues, they'll report on advances in science, they'll report on trends in medicine or whatever. And they have lovely graphs and they have lovely writing. And they can take something about vaccine development, and you can read the article about vaccine development, and you'll have a very good idea of the issues and what was going on. So this was held up to us as a way to learn, was to read The Economist regularly and look at not just what the article says, look at the way they're presented information, at the graphs they use, and the way they've explained it. And this was held up to be, certainly when I was at Gulf, this was held up to be the standard to which we should aspire. This was the thing. So to directly answer the question, my biggest challenge has been learning communication skills.
Ingeniero Álvarez, Álvaro, perdón, también hay preguntas en la otra diapositiva.
We have some other questions.
Yeah.
Please, Professor Michael. From Elisa Rios. It's a very particular question. If we didn't measure the K and G parameters at laboratory because we didn't have vendor elements, what how you recommend there in order to estimate those parameters?
Oh, you mean elastic properties, right?
Yes.
There's actually quite a literature or literature. There are a number of papers where people have reported values, and even though you might say they depend very much on the fabric of the particular situation, I think you can look at similar soils under similar depositional conditions and find some examples and then use that data. If you remember the slide I showed with the data from our site, and then I put on the guidelines for Erksack sand, which is a quartz sand, it wasn't far out. So, you know, look for, and plenty of people are now publishing GMAX studies. So just look through our journals and find some GMAX study similar soils. What I'd also suggest, if within any particular consulting company, you make an effort to put your various data sets into one spreadsheet for your engineers. You know, any individual engineer in a company should not have to do this for themselves. As a company, you ought to know within your group, you know, okay, you know, here's 10 case histories we've downloaded, plot them up in Excel, let's make them, let's share it. So that's where I would go.
Thank you. Yes, thank you very much. I have another question about modeling. Does the calibration of the constitutive model depend on the type of load to be applied, monolithic or cyclic?
Cyclic loading gets you need additional parameters. The procedure I have seen most people using now for cyclic loading is they do cyclic simple shear tests, or cyclic direct simple shear tests, and they then calibrate directly to those. In the case of Norsand, we pick up a rotation parameter, and you need to kick that in. You'll find the FLAC implementation of Norsand, I think, has got the principal stress rotation parameter into it. If you again Google, I think if you just Google principal stress rotation, you'll find the paper I wrote on how to do this. It's a free download. I think principal stress rotation and possibly my name will find that paper for you.
I think someone tried to download this article, but he or she could find it. Maybe you could help us type in the website.
We know some of the people who are supposed to put up source code. Some of the websites, one of the websites has disappeared, and one of the websites, the download procedure doesn't work very well. The best thing to do is email me, and you've got my email. It's actually, most of the stuff is my co-author Dawn Shuttle, so I'll just forward it to Dawn. Or you can, if you look at the Tar Island paper, Dawn is the first author of that paper. If you email her, she'll give you the links to the widget and anything else you need.
Thank you.
In fact, I like that suggestion best. Email Dawn.
Okay. Well, I think we have time for one last question. It's from, let me see. Well, Edwin Alonso said that I want to know if it is possible to model dynamic liquefaction with Norsand. If so, are there some recommendations which we have to consider in order to represent this scenario?
Again, the first recommendation is go for that principal stress rotation paper, because that's where we set out how Norsand is extended to do cyclic mobility. Okay. And that tells you the parameter to pick up, and that is what you'll find in FLAC. So I don't believe it's been implemented in any of the other software. I don't know about, I'm not sure about RS2, but Plaxis certainly doesn't have the cyclic one in. Now, having said that, it doesn't do a bad job, but it's doing 3/4 of the job, because you'll find when you look at the principal stress rotation paper, we say there's actually something still missing. And that thing that's still missing is what we're trying to add in Plaxis right now. So at some point, this cyclic stuff will be in Plaxis and presumably in FLAC as well. But where we're at, we know how it works. We know what's going on. We can get an awful lot right, but we can see something that's not quite perfect. And I rather like getting things perfect because it's very obvious what's missing. And I'd like to add that little missing bit. But anyway, the current status is FLAC will do it for you. There's a paper that tells you the background. Yes, I'd love to see you write up as a case history or description.
Great. Thank you very much. Maybe you have some book at the basis of this amazing subject that you could recommend to all these students to start.
Right. There's what I would suggest you do. Of course, I could say go buy a copy of my book, right? But that, in all honesty, that book is written as a reference text. It's used by some universities for teaching, but it's not. It's for a later stage in your life. It's not when you're in the learning module. If you go to the Vancouver Geotechnical Society website, in Vancouver in Canada, we did 2 courses for them on critical state soil mechanics. If you go to the 2020 course, you will find the course notes, which you can download as a free download. Those course notes are fairly close to a 1 semester undergraduate, postgraduate course on critical state soil mechanics. And there are also, there are teaching example and tutorials, spreadsheets, so you can teach yourself. So in principle, if you're prepared to spend a weekend, you can download what you need from Vancouver Geotechnical Society, and it will lead you through the ideas I presented to you in the last hour.
Okay, thank you very much. Yeah, it's important. Okay, thank you very much again, and we are keeping in touch because we think that you could you need more time for share all your knowledge, and maybe we could organize another seminar, maybe a course or something. Thank you very much. Chris, maybe.
Yeah. Thank you very much, Engineer Mike. Really, thank you very much for sharing your knowledge. We, as I said, we are very thank you, and yeah, that's it.
I hope you all enjoyed it.
Yeah, thank you
Very much.
Yes, definitely.
Okay, guys, it's time for me to have a glass of wine.
Yes. Thank you very much.
Bye, guys.
Bye.